Assalamu alaikum. So we've already come to grips sort of with the uncertainty principle, and we've looked at different manifestations of the uncertainty principle. One last example that I would like to share with you is that if you have matter that is inside a volume, and you squeeze the volume, but the matter remains the same, the amount of matter remains the same, then it's fine. You can squeeze it even further, you'll be fine, no problems. But you keep on squeezing this volume and keep the amount of matter the same. A certain point will approach when as you keep on squeezing this matter into a smaller and smaller volume, which means you're confining the matter to a smaller and smaller volume, the uncertainty in its momentum keeps on increasing because of the uncertainty principle, which means that its momentum really keeps on increasing, which means that its energy keeps on increasing. So it becomes difficult to restrain the matter, it becomes difficult to confine the matter because it has very large energetic tendencies to explode, to fly apart. So its energy goes up, and this is a direct manifestation of the uncertainty principle. So it's difficult to confine matter, to confine or to squeeze matter. And this is a direct result of the uncertainty principle. So one example I would like to share with you, and I've already hinted at before, is suppose you have a nucleus inside an atom and you have an orbit. The Bohr's orbit of radius r is Rn. So this is the nth orbit, okay? And then you have a neighboring orbit of radius Rn plus 1. So Bohr's model says, please be quiet. Khamosh. What Bohr's model says is that the electron, if it is in the nth orbit, it is doomed to remain in the nth orbit forever unless a transition takes place. So the electron is confined to this orbit. An electron that is in this orbit will always remain in this orbit unless a vacancy is available so that it can make a transition. And there are many orbits in between. So this is just the nth orbit, this is the n plus 1th orbit. So let's be a little bit more generous and say that, okay, let's confine the electron not to this orbit, but let's confine the electron to the region between these neighboring orbits. Okay? So the electron is now confined to exist in this region. And what we would like to say is, what we would like to see is whether this is possible or not. Can we confine an electron to a small region inside the atom? Alright, so for this purpose, we'll have to find out what the energy of this electron is if it were to be confined in this region. And we'll use the uncertainty principle to find this energy. So from the Bohr's model, we already know that the nth radius is given by 4 pi epsilon naught h bar square m e squared n squared. This is something that we've already derived in our discussion of the Bohr's model. Can you verify that I've written the correct relationship? Can you look up your notes if you have the correct relationship, please? Correct. So this is the radius for the nth orbit. Now the electron is somewhere in between these orbits. So we have confined its spatial position. The range of possibilities of its spatial position is between Rn and Rn plus 1. Okay, so what is the realm of possibilities for R, delta R. What's the range of possibilities? So it's Rn plus 1 minus Rn, and this equals 4 pi epsilon naught h bar squared m e squared. N plus 1 means n plus 1 squared minus n squared. Okay, so this becomes 4 pi epsilon naught h bar squared over m e squared. This is simply n squared plus 1 plus 2n. So the n squares cancel out, you left with 2n plus 1. Okay, and if n is large, suppose n is large, if n is large, 2n plus 1 will almost be 2n. So we just simplify the calculation a little bit. Okay, if n is large, this will hold true. So under this condition, you put a 2n here. So this is the uncertainty in the position of the electron. Now we have to find the uncertainty in the momentum. So we use the uncertainty principle. Delta R, delta P has to be greater than or equal to h bar over 2. So let's use simply h. It doesn't really matter if you use h bar over 2 or h, because they are of the same order of magnitude and we're making an estimate anyway. So I use h. If you use h bar over 2 or h bar, that's also fine. I'm using h. So this means that our uncertainty in the momentum, delta P, has to be greater than or equal to h over delta R, which equals let's use h. Let me see what is more convenient. We can use h bar as well. I just want to make the calculation simpler.
So if you use h bar, you can answer to
Let's use h bar. Just to make the calculation simpler, I have delta P greater than or equal to h bar over delta R. So h bar delta R is this much. So I have h bar m e squared 4 pi epsilon naught h bar squared 2n. So I make this 8. This h bar cancels out. I'm left with an h bar here. So this is the uncertainty in the momentum. Okay. Now I can also find the uncertainty in the energy. If I were to make this assumption that E equals, the energy is, all of it is kinetic energy, because the electron is far away from the nucleus, the potential energy is close to 0. The energy is, all of it is kinetic energy, and it's given by P square over 2m. So this is just my assumption, G. So if this is my energy, then my uncertainty in energy is going to be 2p delta P over 2m, 2p delta P over 2m is P over m delta P. So this is my uncertainty in energy. This is my delta P. But what is P over m? This is the velocity of this electron, the speed of this electron. We're not considering the relativistic energy. This is just an assumption. We're giving an order of magnitude estimate. So P over m is the velocity of, or the speed of this electron as it is inside this region, as it inside these orbits. But we know from the Bohr's condition that mvr equals nh bar. The angular momentum equals nh bar. We know that. Do you understand where this relationship comes from? Because we haven't discussed where this relationship comes from. Now this has a very interesting origin. This relationship has a very interesting origin. बातें ना करो, चलो मुझे भी बताओ. वो दोनों साइड्स के डिफरेंस की ले लिया ना, 2p डेल्टा p आ गया. अच्छा, a small digression. डाइग्रेशन का मतलब ये है कि हम किसी मंजर की तरफ जा रहे हैं, रास्ते में एक और खूबसूरत मंजर आ गया, हम थोड़ी देर उसको देखने के लिए रुक रहे हैं. तो ये जो रिलेशनशिप है, which is the Bohr's quantization of the angular momentum, this object we know is the angular momentum, and this is telling us that the angular momentum is quantized. In fact, de Broglie, Bohr proposed this relationship, but he did not give a reason why he proposed this relationship. It was de Broglie who made sense of this relationship. What de Broglie said is that if this is mv, this is the momentum p of the electron, but the momentum p is given by h over lambda, according to the de Broglie relationship. So h over lambda into r equals nh bar, and nh bar is nh over 2 pi. So I take this 2 pi to the other side, this h cancels out, 2 pi r equals n times lambda. So if the electron was moving in a circular orbit around the nucleus, I had a nucleus and an electron was moving in a circular orbit around the nucleus as in the Bohr's model, and this radius is r. Could you tell me what is the meaning of 2 pi r? It's a circumference. It's the length of this circle, and this length of the circle contains an integer multiple of wavelengths. This means, and this is the wavelength of the electron wave, of the matter wave associated with the electron, of the pilot wave associated with the electron. What this means is that inside this length, an integer number of wavelengths fit in. 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, 5 wavelengths. It could have 4 wavelengths, 5 wavelengths, 3 wavelengths, 1 wavelength, and so on. This condition has to be satisfied. Otherwise, destructive interference between these waves is going to take place. In this condition, standing waves are formed. So, in order for the formation of standing waves, this has to be satisfied. And for this to be satisfied, this has to be satisfied. So this is the origin of the Bohr's angular momentum quantization condition. So if we use this condition, our V turns out to be nh bar over mr. And I can put a small n here to denote that this is the nth orbit. So I use this value of V and I put it into delta E. Okay? So my delta E comes out as V. V is given by nh bar over mRn multiplied by delta P. Delta P is given by this, m E squared 8 pi epsilon naught h bar n. So this n cancels out, this h bar cancels out, and I want to eliminate this Rn. This Rn is given by this expression. So I do a little bit of algebra. I get m, this m also cancels out. I get E squared 8 pi epsilon naught and Rn is now equal to m e squared 4 pi epsilon naught h bar squared n squared. Okay, so this is my uncertainty in energy. I've just done algebra, and if I do a little bit of simplification, this turns out to be m e4, 8 4s are 32 pi squared epsilon naught squared h bar squared 1 over n squared. This is my uncertainty in energy when the electron is confined to reside always in this region. This is my uncertainty in energy. Does this expression look familiar? Alright, if it doesn't look familiar, can you please, I give you 1 or 2 minutes, can you please calculate the value of this constant? Okay, I can write down the constants for you. Can you please calculate this constant for me? I want you to do it. It looks a trivial exercise, but I want you to do it. Zero?
The calculator would limit the answer. So it gives a 0 because the calculator would not be able to calculate it. Such minute number.
It's not really minute.
It's very minute. So 10 raised to the minus 92 is the power 4 into 10 raised to the minus 31.
Can I see your calculator, please? Okay, you're calculating the numerator first.
Yeah.
That gives you 0. But calculate the denominator first and then take the inverse and multiply. Has anyone been able to identify what this constant is? It's not the Rydberg's constant. क्या आ रहा है? 13.5 क्या units है? Electron volts. So this number here is 13.6 electron volts. You can look up your notes from the Bohr's model as well. It's the same constant that we've derived. The energy for the electron in the nth orbit. So this uncertainty in energy is 13.6 over n squared electron volts. This is the uncertainty in the energy. Okay? Now what is the energy of the electron when it is inside the nth orbit. What's the energy of the electron inside the nth orbit? क्या होती है एनर्जी बताओ? nth ऑर्बिट में इलेक्ट्रॉन की क्या एनर्जी होगी हाइड्रोजन एटम के अंदर? ऊंची बोलो. n कहां गया? मल्टीप्लाई बाय. नहीं पूछना पड़ता है, क्या करें? क्या एनर्जी है nth ऑर्बिट में इलेक्ट्रॉन की? 13.6 over n square electron volts with a negative sign. Okay, so when the electron is inside the nth orbit, its energy is minus 13.6 over n squared electron volts. But what is the uncertainty in the energy? It's this much. So the uncertainty in energy is almost the same as the energy itself. What does this mean? This means that the real actual energy of the electron, can be of the order of, can be as big as uncertain as the nominal energy, the expected energy, and the uncertainty plus delta E. And this will give you 0, which means that the electron is now outside the confines of the atom. Its energy is 0. It has been ionized. Since the uncertainty in energy is almost as big as the energy itself, this means that the electron can be ionized, because this is also the ionization energy of the electron in the nth orbit. So what does this mean? This means it is impossible to confine the electron inside this region. It's impossible to confine the electron to this radius. It's impossible to confine the electron to any radius. If this region were even smaller, what will happen to the uncertainty in energy? Will it increase or decrease? It's going to increase. So it becomes even more difficult to confine the electron to this small band. If I were to say that the electron is doomed, is destined by fate to exist always inside this orbit, is it possible by uncertainty principle? No. Therefore, Bohr's model, which was presented in 1913, which put electrons in discrete orbits at particular radii away from the nucleus, is flawed, has serious errors in it, has serious shortcomings in it, and that was called the old quantum theory. What we now know is that the electron is not inside this orbit, or it's not inside this orbit, rather the electron is a field. Denoted by the wave function psi. It's a field and it spreads out in space. And when we're talking about electrons inside the hydrogen atom, then these fields are called orbitals. So the electron really does not belong to any one position. Its radius is not fixed. Its distance from the nucleus is not fixed. We should stop thinking of the electron as a particle. It is really a field that fills up all of space inside the atom. It's everywhere. And when you observe the electron, you collapse this wave function onto a certain point, onto a certain position. And these orbitals have shapes of different kinds. And since the hydrogen atom is of course a three-dimensional object, ये तो मानते हो ना 3 डायमेंशनल, तो ये ऑर्बिटल्स, ये फील्ड्स भी 3 डायमेंशंस में एग्जिस्ट करती हैं. फॉर एग्जांपल वी कैन हैव एन s ऑर्बिटल. दिस इज एन s ऑर्बिटल. दिस इज अ पिक्चर ऑफ द फील्ड फॉर एन s ऑर्बिटल. It's spherically symmetric. I'll show you simulations of these orbitals, but what this means is that the electron is, what does the s orbital mean? Let me tell you qualitatively what it means. You have the nucleus, and what I want to draw is the field of the electron when it is in the s orbital. हाइड्रोजन एटम में अगर एक इलेक्ट्रॉन है जो होता है वो s ऑर्बिटल में होगा ना, ठीक है. तो अब उसका वेव फंक्शन बनाना है. 3 डायमेंशन में वेव फंक्शन बनाना मेरे लिए मुश्किल ही नहीं, नामुमकिन है, बट आई विल ट्राई. सो आई वुड लाइक टू ड्रॉ द फील्ड ऑफ द इलेक्ट्रॉन इन द s ऑर्बिटल. व्हाट द फील्ड लुक्स लाइक द फॉलोइंग. इट्स जनरली आल्सो कॉल्ड अ क्लाउड. Cloud means that the field is everywhere. So I just draw the field by shading. I shade with the help of chalk. I shade the regions around outside this nucleus, and the level of shading tells me how strong the field is. Okay? So this is a picture of the field to the best of my abilities that I can draw. It's not in fact the wave function. I've drawn the probability density function. If I were to draw the wave function would look like this. This is a picture of the wave function for the electron in the s orbital. This is a picture of the probability density function for the electron. If I do not look at the electron, the wave function, a snapshot of the electron is this. If I take a picture of the electron with some hypothetical device and I would like to picture what the wave function looks like, it's going to look like this. In 1 dimension it's easy to draw wave functions. But in 3 dimensions, the wave function is actually a field that fills out space in 3 dimensions. It's a cloud in 3 dimensions. So in 3 dimensions, and I take a projection on 2 dimensions, this is what the wave function will look like for an s orbital. And the electron is really everywhere. It fills up all of space because you're not looking at it. Once you want to find out the position of the electron, you will use the probability density function, which is proportional to the modulus squared of this wave function, and this is what you will get. And what you will observe is that the probability density function starts off by 0 here, it increases, goes to a maximum, and then decreases again. If this is the radius r, And if I would like to take a cross section of this field, I take a cross section or a profile of this field, I would like to map out what the field looks like as a function of r. Then the wave function goes like this for the s orbital. It's maximum at the nucleus. The wave function is maximum at the nucleus and then it decays exponentially. Here the shading is maximum at the nucleus. नजर आ रहा है ना शेडिंग मैक्सिमम में. यहाँ पे वेव फंक्शन की मैक्सिमम एम्पलीट्यूड है and then it decays exponentially as we go away from the nucleus. And if I were to plot the probability density function, now these are just pretty pictures that I am drawing, but they have a lot of meaning. What I am plotting here is now as a function of r, I am plotting a probability density function which is given by psi mod squared multiplied by r squared. So what's the origin of this r squared? I think it's beyond the scope of a freshman modern physics class, but we're taking when you study calculus 2 it will become clear. But the probability, this is the probability density function, and this probability density function starts off from 0 at the nucleus, goes to a maximum and then decreases, and this maximum turns out to be equal to the Bohr's radius A0, 0.5 angstrom units. So let me recap. गौर से सुने. In the old quantum theory proposed by Niels Bohr, the Danish physicist, in 1913, the electrons were confined to remain inside the orbits. Heisenberg came and presented the uncertainty principle. He stated that if you confine the electron to small regions, its energy blows up. So you try to squish something or squeeze something, the energy due to the uncertainty principle goes so high that the atom explodes. Therefore, the electron does not exist inside an orbit. You cannot say that the electron is always inside this region. So you have to stop thinking of the electron as a particle at a certain point in space, which is moving. The electron is in fact a field. It's a ghostly field, an eerie field, which is called the wave function, that fills up the entire space that is available to it. An example of such a field is the s orbital. These fields inside the hydrogen atom, they are called orbitals. Now this is an example of the s orbital. The wave function is maximum at the nucleus. This is an example of the probability density function. The probability of finding the electron at the nucleus is 0. Okay? Then the probability goes up. It maximizes at the Bohr's radius. So there is some satisfaction for Mr. Niels Bohr in his grave that the Bohr's radius that he presented has some significance. It is reconcilable with the new quantum theory, because the most probable location for the electron is where the probability density function is a maximum, and that is at the Bohr's radius, or the expectation value of the position of the electron is the Bohr's radius, and then the probability density function decreases again. So these wave functions of electrons inside the hydrogen atom, they are called orbitals, and we can have different kinds of orbitals. We can have s orbital, we can have a p orbital, and 3 kinds of p orbitals roughly. We can have d orbitals, and so on. So these are pictures of the orbitals or the electron wave functions inside a hydrogen atom, and these orbitals are everywhere, and these contours these contours that I've drawn. Do you know the meaning of contour? A contour is an outline. You see, an s orbital is really this wave function. There's no quiz today, by the way, Vakar. So this is a wave function, and I've represented this wave function by this contour. Okay, ये एक outline मैंने बनाई है इस wave function की. So you should understand that every picture that I draw is limited in the sense that it means special things in special ways. So this is a contour. Okay, a contour diagram of an orbital. This is a pz orbital, a contour diagram of a pz orbital, which means that the electron can be found. This is telling you the probability of where you can find the electron, but it's really everywhere. Before you measure the electron is everywhere. Once you measure it, there's a probability of where you can find the electron. Now in this pz orbital, the electron can be found with the highest probability inside this region or inside this region, and with very little probability perpendicular to this orbital, right? So if I draw a plane that is perpendicular to this orbital is vertical, and I draw a horizontal plane, there's very little probability that the electron can exist inside this plane. Which means, in other words, if I measure where the electron is, hardly will I see the electron in the horizontal plane. And I will never see the electron at the nucleus, because the wave function is 0 here. The probability density is 0 here. And this point, as you all know from your chemistry, is called a node. And this plane is called a nodal plane. Now the question I would like to ask you, and you should raise your hands and then I'll answer your questions. If you look at this orbital, the diagram of this orbital, the electron is in the top lobe or in the bottom lobe. It's never at the node. You can never trap the electron at the node. You make repeated measurements again and again on multiple p orbital electrons. You will never find the electron to be at the node. So how does an electron, there's a single electron, how does it go from the top lobe to the bottom lobe? एक तीर फेंकता है एक शिकारी किसी जानवर को शिकार करने के लिए, वो तीर फेंकता है, तो उस तीर को मैं कहीं भी पकड़ सकता हूं. An electron that is thrown from the top lobe, I can trap the electron anywhere in its transitory route to the bottom lobe. So I can trap it in principle at the node as well. So why can I never find the electron at the node? G. बिल्कुल ठीक कह रही हैं. इलेक्ट्रॉन तीर नहीं है. The electron is not a particle, it's a field. We should stop thinking of the electron. You should stop asking the question, where is the electron? Because the electron does not have one position. So this question is bogus in quantum mechanics. You cannot ask, where is the electron? You cannot ask how the electron is moving from one point to another, because at any one instant the electron is actually everywhere. It's a field that is smeared out in space. So you cannot ask the question that the electron is moving from the top lobe to the bottom lobe. The electron is actually everywhere. Once you measure it with some probability in the bottom lobe and some probability in the top lobe. So this is what the hydrogen atom orbitals qualitatively mean. But let's give a little bit of more mathematical rigor to the wave function concept. But before that, I have to answer a question.
Sir, keeping this concept in mind, protons and neutrons also be fields, and how do we confine a nucleus to a specific point and then relate the position of the electron to that?
कल की ट्यूटोरियल में थे आप? अच्छा, आप दूसरे सेक्शन में. इन्होंने पूछा है, बड़ा अहम सवाल पूछा है जो आप सबके काम आएगा. वो ये पूछा है कि प्रोटॉन और न्यूट्रॉन भी फील्ड्स हैं. बिल्कुल, प्रोटॉन्स आर फील्ड्स, न्यूट्रॉन्स आर फील्ड, are fields. Neutrinos are fields. Mesons are fields. Bacteria are fields. Most microscopic particles, they act like fields. All of them are fields. Now the question is, how can the neutron be confined to the nucleus, or how can a proton be confined to the nucleus? All right. So if I draw the nucleus of an atom and a hypothetical proton inside, just for illustration I draw it as a sphere. This is a proton inside the nucleus. Now if this proton has to go out of the nucleus, it has to overcome a binding energy. There is an equivalent of the ionization energy for the nucleus as well. Okay? Now that is very high. If we confine the neutron to this nucleus, it will have very high energies. This neutron will have very high energies because we are confining it to a smaller radius. This nucleus is about 1 femtometers in radius, 10 to the power minus 15 meters. So now you're confining the neutron to a very small radius, which means its energy must be very high, right? For the electron that is confined to orbits, the energy is of the order of tens of electron volts. This energy is of the order of mega electron volts. Okay, so if this energy is higher, and if it exceeds the binding energy for the nucleus, this neutron cannot be trapped inside the nucleus, and this nucleus will be unstable. Such a nucleus is called a radioactive nucleus. It will disintegrate and give off particles of different kinds. But if the binding energy is greater than the energy of this neutron, as computed by the uncertainty principle, the neutron can remain confined. So if you have large atomic numbers, generally the nuclei are unstable because the proton energies and the neutron energies are sufficient to overcome the binding energies, and there are strong nuclear forces as well that are gluing the neutrons and the protons together. G.
Answer shows the fields of particles are getting replaced in the protons and neutrons, and showing the field of all protons and neutrons interfere with.
Yeah, they interfere with each other.
Wouldn't that lead to the destruction of the field?
So what that causes is a neutron is converted into one particle, and the particle is converted back into the original particle. So there are oscillations between the particles, neutrino oscillations and so on. G.
So doesn't this conflict with the Geiger-Marsden experiment, which said that most of the atom is empty? In fact, most of the atom has the electron field, so when you throw alpha particles at it, they should repel it, right?
Alright, so a beautiful question is that doesn't all of this contradict the Geiger-Marsden experiment? Because the Geiger-Marsden experiment tells us that most of the atom is empty. But what we've seen is that the electrons are actually everywhere. They're not confined to small radii, small orbits, thin, fine orbits. That's your question. So the point is, when alpha particles, they are coming in contact or they are encountering the atoms in the gold foil, you are making a measurement. When you are making a measurement, there is a probability of where you can find the electron, and that probability is maximizing at what we call the Bohr's radii. Alright? So any act of measurement or observation leads to the collapse of the wave function, and the collapse happens according to the rules of probability, and those probability rules tell us that the collapse is going to happen at the Bohr's radius. It's going to happen at the L shell, at the M shell. The maximum probability is going to occur there. That is why the act of encountering an alpha particle with an atom is akin to a measurement process. Okay? Khamosh, sune baat. These questions give me food for thought for the quiz. No, you should ask questions, but you should listen to the answers. Alright, so now I'm going to be a bit more rigorous, and I ask you to revise your concepts from differential equations. What I'm going to write on the blackboard is something very interesting now. Now please look at this equation carefully and write it down on your notebooks. And reflect upon it. Just think about it. What does it? Just think about the symbols. I'm not teaching you numerology or symbology, but just look at the symbols here.
What will be V of x?
Potential energy. So Schrodinger was also a philosopher of life. He wrote a famous book, What is Life? So apart from his interests in physics and the quantum theory, he would also dabble into the philosophy of science. So it's a very small, nice book which is quite an interesting read. But what we are concerned with today is the equation that he gave, which is called the Schrodinger's equation. Now, his equation is a watershed in the history of physics. Watershed का मतलब you cross from one land into another land and you see a new world altogether. Bohr's theory was the old quantum theory, which confined electrons to orbits, like the heliocentric view of the universe. The Earth, the Sun is at the center of the universe, and the planets are doomed to move in orbits around the Sun. So Bohr's model was a planetary model. Rutherford's model was a planetary model. ठीक है? लेकिन Erwin Schrodinger and Heisenberg changed the view of physics. Schrodinger, जो Heisenberg ने uncertainty principle मुतारिफ कराया, which is a result of matter waves and the conjugacy of position and momentum. और uncertainty principle ने ये हमें सबक दिया कि nothing is certain in physics. There is some intrinsic uncertainty, and that intrinsic uncertainty, as I mentioned, is a realm of possibilities. It presents not a limitation but an opportunity. ठीक है, ये बात आप समझते हो ना कि आमतौर पे uncertainty का लफ्ज negative connotation रखता है. It has some negative meaning, uncertain. But uncertainty principle does not really mean that physics is more uncertain. It just means there's a huge array of possibilities that you can observe. And what do you really observe becomes probabilistic. Okay? So now physics has a probabilistic viewpoint. You can have a probability that you detect an electron at position 1 centimeter. You have a probability you can detect an electron or a photon at position minus 3.2 centimeters. So it becomes probabilistic. Okay? So now with the help of Schrodinger and Heisenberg, thanks to them, quantum mechanics or physics is now probabilistic. तो जो deterministic viewpoint है ना universe का, deterministic viewpoint है universe का. एक फ्रेंच साइंटिस्ट था लैप्लास. इलेक्ट्रिकल इंजीनियर्स की बड़ी दोस्ती हो जाएगी लैप्लास से. तो लैप्लास ने एक फिलोसोफर भी था. फिजिक्स को पहले फिलॉसफी कहते थे, नेचुरल फिलॉसफी. ठीक है, आइंस्टाइन की किताब का भी ये नाम था, प्रिंसिपल्स ऑफ नेचुरल फिलॉसफी, ठीक है। तो लैप्लास एक फिलोसोफर भी था, उसने प्रेजेंट किया था आइडिया डिटर्मिनिज्म। डिटर्मिनिज्म का मतलब ये है कि इफ आई नो द प्रेजेंट आई कैन टेल द फ्यूचर, इफ आई नो द पोजीशन एंड वेलोसिटी in the present I can tell where the particle will be in the future, and I can tell how fast will it moving be in the future. That is what enabled astronomers to make tables of planetary motion. They can predict that there is going to be a solar eclipse on 13th of June 1736 AD, because they can predict the future, because they can measure what's happening in the present. They know what the position of the planets is in the present, what speed are they moving at, so they can predict what the future is. So they can make these elaborate astronomical tables. This is called determinism. You can tell the future by looking at the present, by looking at the position and velocity in the present time. And if you know the present, you can predict, or you can post tell what happened in the past. So this is the deterministic viewpoint of the universe. But with Schrodinger and Heisenberg, we have to say no to absolute determinism, because everything is now probabilistic. But that does not mean we have less knowledge about the universe. It actually means we have more knowledge about the universe, because there is a realm of possibilities now. Okay? So that is why when we learn about modern physics, it's intertwined with a little bit of philosophy as well. And you cannot learn modern physics by ignoring the history of physics, the history of science, and how human mind progressed through the ages. So if you look at this equation, it looks like a daunting equation. But my task as your teacher is to make this simple, to make this look simple to you, so that you can understand what it means and be able to solve this equation in a few select cases. But let's look at the symbols first. H bar, we all know, the reduced Planck's constant. Suppose we focus on the electron for the time being. M is the mass of the electron. This is the double derivative. Do you all know what the double derivative means? It's with respect to x. This is the potential energy of the electron, V, and it's a function of x. Iota is the square root of -1, the reduced Planck's constant, the derivative with respect to time. Okay? And this object looks familiar, it's the wave function. Okay? Now the wave function I've written with two variables. This is a space variable, and this is a time variable. The wave function exists in space and it can change with time. Okay? So it must depend upon x and on time. There are two variables. And this is the potential energy. We assume that it only depends upon space. It does not change with time. Okay? Now when you become physics majors and refined electrical engineers, you will often write this equation in the following form. Alright, you can often in your book, perhaps in survey's book or in other books, you can often find this equation to be written in this form. It's just a different way of writing the equation. You take this psi at the very end, right, and you write it just like this. So this object is called an operator. It's an operator. and this object is the operand. There's an operation that is acting on this operand, and the machine that is making this action is called the operator. So this is an operator acting on an operand. आज डाकू दे है ना, तो ये एक शिकारी है, ये और ये उसका शिकार है. So this is the prey to this hunter. So this is another way of writing this equation. So let's talk a little bit about this wave function. What the Schrodinger equation tells us is, in the classical world, if I write F equals ma, this relates the acceleration of a particle with the force acting on the particle and the mass of the particle or the object. Can you derive this equation? No, it's empirical, right? Empirical का मतलब ये observation से हमें नजर आती है, और इसका कभी इसके बरखिलाफ कोई चीज नजर ही नहीं आई कि हम कह सकें ये गलत है. Okay, you cannot derive this equation from anything simpler. It's an empirical fact of life that F equals ma must hold true. Likewise, you cannot derive this equation from anything simpler. It's an empirical equation. You can motivate it. You can satisfy yourself that it is correct. You can do all kinds of mathematical ramblings to satisfy that this is correct, but it cannot be derived from anything simpler. Alright? Now the operand in this equation is the wave function. This is the field of the electron, of the photon. It's a matter wave. And this equation tells us how does this wave function change with time and with position. You solve this equation and what will your result be? If, first of all, is this a differential equation?
Yes.
यार फोन्स की इजाजत नहीं है क्लासरूम में, और फोन्स में हर तरह के फोन शामिल हैं. Any electronic device that can make contact with the external world is not allowed. Okay? अब बाज नहीं आ रहे. First of all, is this a differential equation? Yes, because it has derivatives in it. This is a derivative, this is a derivative, so it's a differential equation. Second thing, it's a strange equation because there's a complex number in it. There's an iota in it. Probably this is the first time you're seeing a differential equation or any equation with an iota in it. Probably. Another strange thing about this equation is that on the left hand side there is a derivative with respect to x, okay, and on the right hand side there is a derivative with respect to time. So if this is a differential equation, it has some complex coefficients in it and it has mixed space and time. Okay, and another thing, this wave function, is it a real number, imaginary number, or a complex number in general? In general, it is a complex number. It can be real, it can be imaginary, but in general it's a complex number. So psi xt is complex. So every equation has to be solved. If this differential equation is solved, what will be the result? What will the result tell me? If you look at this equation, F equals ma. Ma is m d square x over dt. t square. X is a function of time. Now this f is something, okay? If I have a mass that is attached to a spring, and this mass is at its rest, and I move this mass towards the right and I let it go, it's going to oscillate back and forth. It becomes an oscillator, a harmonic oscillator. So for this system, what is the force equal to? What's the force for such a system? It's minus kx, Hooke's law. So for this kind of system, I have this equation, minus kx. So the equation becomes, this equation can also be written as m d square x over dt square plus k x equals 0. Now this is also a differential equation, but everything is real here. X is real, m is real, k is real, but it's a differential equation, and x only depends upon the time, so it's not mixed. Now if I ask you to solve this equation, what will the solution tell me? I mean, I'm not asking what the solution is going to be, but what is the meaning of solving this equation? हाँ आप बताइए. Right. So what we will obtain is, how does x depend upon time? This variable x and its dependence on time will be a solution of this equation. Okay? And then I can plot the solution. So I have time on this axis, I have x on this axis, and I can plot the solution. This is a plot of the solution. Okay? So solving the equation means finding what x is and how does it depend upon time. Now if you look at the Schrodinger equation, what is the meaning of solving this equation and what would the solution result in? अब लास्ट रोज में से प्लीज बताएं मुझे क्या मतलब है सॉल्यूशन फाइंड करने का. आप बताओ आपको हार्मोनिक ऑसिलेटर वाली बात समझ आई है या वो भी नहीं आई? वो आई है समझ? ठीक है, आप बिल्कुल अपने जहन को थोड़ी सी वर्जिश दो, थोड़ा सा एक कदम और चलना है. अब बताओ कि उसका सॉल्यूशन फाइंड करने का मतलब क्या है? एक्स तो है ही नहीं, एक्स कहां पे है? नहीं, सॉल्व करने के नतीजे में आपके पास क्या चीज आएगी? आप बताओ. एनर्जी. चलो आप बताएं. Right. So the solution of the Schrodinger equation will tell us how does this object psi depend upon x and time. So solving the Schrodinger equation means finding psi. And how does it depend upon x and time? Just like here, solving the differential equation means finding out how x depends upon time. I can write this as some psi. Doesn't really make a difference. So finding the solution means how does psi depend upon time? If I had an x here, it would mean how does psi depend upon x and time. So if I solve the Schrodinger equation, solving the Schrodinger equation SE gives me how psi depends on space x and time. That is, I can find psi x t. Now the wave function has a few interesting properties that you must remember. If I would like to plot psi, I can plot it with x or with time. It's difficult to plot it with respect to both x and time at the same time. Okay? अब ग्राफ बनाते हैं दो वेरिएबल्स के दरमियान. On one axis I have psi, on the other axis I can have x or time. Okay? It's difficult to make both of these plots at the same time. Now the wave function has a few properties. First of all, the property is that psi is finite. Which means that the wave function can never be infinite. Okay? So the wave function has to be finite. This is an allowed wave function. But if I have a wave function that goes to infinity, this is not allowed. And why is this not allowed? Because the wave function modulus squared corresponds to probability density. The probability density cannot be infinite. So psi has to be finite. Number two, psi is continuous. Continuous functions पढ़ेंगे calculus 1 में. So psi has to be continuous, which means discontinuous psi's are not allowed. For example, a psi of this kind is not allowed, because at this point there is a discontinuity in the wave function. This is not allowed. Discontinuous wave functions are not allowed. This is x or t. X or t wave function. This is not allowed as because the wave function is discontinuous here. So only finite continuous wave functions are allowed. The third property is that psi is single valued. What this means diagrammatically is x or t psi. This is not allowed. I cannot have a wave function of this kind, because ध्यान से सुने, because for this wave function, if I choose this value of x naught, then the value of the wave function can be this one or this one or this one. So for one value of x or time, I have three values of the wave function. But this is not allowed, because only single valued wave functions are permissible. So this is not allowed. And there are two more properties, I just write them down. Number 4 is that the derivative of the wave function with respect to x is also continuous And there's a fifth physical requirement. And the physical requirement is that at any time psi x t mod squared dx over all of space, what has this to be equal to? This has to be equal to 1. This is a physical requirement that the probability must be summed to 1. So in Tuesday's lecture, we're going to solve the Schrodinger equation for a particular problem, and we're going to have a demonstration in the classroom as well. So be there. Thank you very much.